Hello physical science students, here's a supplementary video that we've had to make because we've added some new stuff to the syllabus, and so it fits in at 7.8 within the covalent bonding, and it's called fullerenes. What are fullerenes, you might ask? Fullerenes are another class of allotropes of carbon. Remember the other allotropes of carbon? Remember what an allotrope is? An allotrope is something that has the same composition but different structure. And for carbon, we've got diamond, we've got graphite, we've got graphene, and we've also got fullerenes. And fullerenes can occur as either balls or tubes. And this is some pictures of some. Here's a ball which is made up of 60 carbon atoms. This is a tube, and the tube can keep going. It can be quite a long tube, so there's no set size for these tubes. What else do I need to say? And notice that each carbon in these has 3 covalent bonds. So very similar to the bonding that you find within the graphite sheets or within graphene itself. Having 3 bonds though means that there's a free electron, and so these guys will conduct electricity. Now the spherical fullerenes are also called buckyballs, and they're called buckyballs because they're named after a guy, and I'll show you in a sec. I've sort of got this slightly out of order, but I'll show you why. Now, like other substances that have giant molecular structures, now what are other substances that have giant molecular structures, you ask? Well, they're the covalent networks. They're the diamonds, the silica dioxide, the carbon tungsten carbide, a couple other things. So there, where the structure is just repeated and repeated, and you can get thousands, billions, gazillions of atoms all joined together, but you've got that same structure throughout the substance. Now, they all, meaning that they have this repeatable structure of covalent bonds, means that they have very high melting points and boiling points. Now, nanotubes also offer a massive surface area for their size because they're made up of tiny little atoms, and they're very small, but they've also got a large surface area. Now, they were discovered in 1985, and they were named after a guy called Richard Buckminster Fuller, hence the buckyballs, and he was a famous American architect. And he was famous. Why he was famous? Well, he was famous because he made these domes, geodesic or geometric domes, that very much have a similar design structure to what you see in nanotubes and buckyballs. And you can see these structures now still being made. Lots of things architecturally get made with those sorts of structures. But he was the first one to use them. Here's just some pictures of some buckyballs of different sizes, different numbers of carbons, something from I think 50 to 70. Notice they're slightly different, but again the reoccurring shape. Now these all occur naturally. They can be made as well, as can the tubes. Notice that this tube is curved, but they can also be made to be straight. Now, some of the uses of them, they've been around a while. And some of the uses were pretty quick to be put into play. Now, nanotubes are significantly stronger than graphite, and therefore they've been used in sporting equipment to reinforce some tennis rackets, golf sticks, all sorts of things. Sailing masts all use nanotubes to make them even stronger. Because of their large surface area, they can be used as a container for transporting drugs around the body. Here's a nanotube with some agent inside it. Here's a buckyball with an atom inside it. Now, what chemical engineers can do, or chemists can do, is they can take a buckyball and they can attach chemicals to the buckyball. And some of these chemicals may be the sort of chemicals that hunt down and find cancerous cells in a tumour. And so, if these chemicals go to those tumours, what you can do in the buckyball is, inside the buckyball you can put a chemical, or you can put a radioactive atom, and that atom will then decay when it's ready, but it will be decaying right in the tumour and nowhere else. And so, a very practical use of the buckyball system or the nanotube. So they can be used as a drug delivery system. They can also be used, because of their massive surface area, as catalysts. Well, not so much as catalysts, but you attach the catalyst to the tube, which is what's happening in this case here. And also here, this is an example of a catalytic converter. We're using platinum, nickel and magnesium distributed along the nanotube, and you're passing carbon monoxide through it, and you're getting carbon dioxide, which is what happens in your exhaust system in your car. Now, a lot of these have industrial uses, and although they've been around for a while, a lot of those industrial uses are not well known, but are also developing with time. And I should have said that some of the drug uses are still being developed, because there's got to be a lot of testing on those sorts of things before they're actually released. Now, they can be also used in fuel cells, because they do conduct electricity, and there's a bit of a battle now. Some people were saying that the fluorines will be replaced by something like graphene, which has similar properties, and so we'll see whether or not fuel cells have fluorines or graphene in them. But there's a lot of research in them, because a lot of our stuff that is powered by batteries, and we also want to develop fuel cells for cars and vehicles and things like that. So a lot of money is being spent on that sort of research. NASA's developing infrared sensors that use these nanotubes. Here's a very small scanning electron microscope of the nanotubes. They developed a paint that when you paint it on, the nanotubes in the paint all line up, and this surface, when infrared waves hit it, it gets about a 99.999% absorption of that infrared radiation, much more sensitive than other infrared sensors, and so they're using that as a coating for their infrared telescopes and various other sensors that they use to look out towards the universe. Now this is a electron microscope picture of it, and if we blew up a small section of that, we'd see the ends of all the nanotubes are all pointing upwards, and so any infrared goes straight in and gets absorbed. They can also be used in a more practical sense here on the surface, by having a nanotube between two electrodes, and infrared radiation. When infrared radiation hits the nanotube, the electrons flow. Interestingly, the electrons will flow one way, and these quantum thing called holes will actually flow the other way. And a hole is a quantum physics quantity. Basically, it's a spot of nothing where an electron isn't, but they flow the other way. And they'll be starting to come up and have practical uses in the years ahead. Already, nanotubes are being used as strong materials, for example, bulletproof vests. This is a suit that is lined with it, much lighter than some of the other products that are being used. And you can see here why, because of the covalent bonds in the nanotube. They flex, but they also absorb a lot of the energy. Clearly, if you're a modelling this sort of stuff, you're either got to look deadly serious or wear sunglasses. CSIRO here in Australia is doing a lot of research into these nanotubes, and this is their research where they're actually making nanotube fibres, weaving them, and if you go up around in anti-clockwise ways, you get a bigger picture of it. So this is the actual finished nanotube fibre. It's developed by weaving other nanotubes together. These nanotubes are stripped off this surface here, which is full of nanotubes. Very technical way of doing it. Now, just a couple of quick questions that you may be asked about fluorines. One is, write down 2 reasons why nanotubes are used as catalysts. They have a very large surface area, and you can attach the catalyst to the tube. That's a pretty typical question. Another one is, how can the buckyballs or the Buckmeister fluorines are used to cage other molecules? What's the use of caging these molecules? And that's a drug delivery system. So there's a few other things that we can ask you about these guys, but they're going to be some typical ones. So that's it. Cheerio.